Hey folks, welcome to Clear My Paper. Today we would be discussing on Kramer's rule and we'll be focusing on a 2 by 2 matrix. This is more of an algebraic understanding. I'll hopefully put something on the geometric side also so that you can visualize it in your head, get some intuition. And typically whatever I'm going to put here, although it's a short video, for the most of it, the logic behind how Kramer's rule work and where do the formulas come, typically textbooks kind of miss that, and I kind of don't like that. So I'm just putting a kind of a giving some context, and then I'll come to the formula, so which will be kind of easier for you to apply and remember and slightly appreciate why things are done in a certain way. Okay, so let's jump on to Kramer's rule for a 2 by 2 matrix and let's get started. So as a quick recap, in the last videos or in one of the last videos, you must have seen how I kind of defined and derived a determinant of a 2 by 2 matrix, and in the context of solving linear equations with two unknowns, right? And I have copied and pasted the same set of examples again in this video as a recap. And what you would see here is on the left side, I had taken actual examples of two equations in x and y. On the right side, I was trying to generalize the same equation with ABCD variables and trying to solve that. And what we learned is what is highlighted in colors, right, in yellow or red. In this case, we are trying to find the values of x and y. And what we discovered was both x and y kind of have the same denominator. Over here we had 7 and 7. On the right side, it's AD minus BC. It has the same denominator. And the denominator cannot be 0, right? It cannot be 0 for the solution to exist because a 0 in the denominator is not defined. So a denominator cannot be 0 for the solution to exist. And what we kind of concluded was the denominator in this case, AD minus BC, which will appear several times throughout the course of matrices and determinants in various contexts. The denominator AD minus BC is called the determinant because it determines the property of the matrix, or it determines the way the solution of this problem will exist, among many other things. That's one of the biggest factors, that it talks about the property of the matrix in terms of what is the potential solution, or how does the matrix do the transformation. That's what we kind of did it, kind of a quick recap. I don't want to get into the details. So that's what we did it, right? And we'll kind of slowly start from that point. And remember this example is going to be taken throughout the rest of the syllabus for you to explain. So a lot of things will be going back and forth. It might appear repetitive, but it's not repetitive. We are just trying to take the same fundamental example that I've explained, and we are trying to explain different things like an inverse of a matrix, what is a minor cofactor, the remaining part of the syllabus. So just hang on with that, and that will nicely tie out the same example explaining different things and different syllabus. Okay, so let's get into the next part. And then we also discovered that if the matrix within the square brackets is ABCD in matrix donation, denominator will be, a determinant will be between the two vertical lines, and it will be written ABCD. And we'll always multiply in terms of finding the determinant of a 2 by 2 matrix. We'll always multiply the two diagonals. First, we'll multiply the diagonal which is on the backslash, like this one, minus, we'll multiply the elements on the forward slash or the other diagonal. That's how we're going to multiply that. That's what it means, straight away drawing from this denominator, AD minus BC. Okay, now what I'm going to do is I'm going to take these highlighted portions and I'm going to rewrite and try to explain where does a Kramer's rule kind of fit in. So I've taken the same set of equations from the top on the left and right. I've removed all the unnecessary computation and kept whatever is required. On the left, I've kept the actual numbers. On the right, I've just kept whatever is required. So we have two equations here which are given, and then we have the value of x where the denominator is AD minus BC. We have the value of y where the denominator is again AD minus BC, and both the denominators are same. So we are going to start from here so that we don't have to create too much of line items and get confused. Okay, so let's just focus on this part and then we'll come to this part, right? On the left side, first focus on the right side, the generalized equation, and then we'll come back to the left side as an example. Okay, so what I'm doing here, both these examples over here, right, whatever I've written on the left and whatever I've written on the right, I'm denoting them in a matrix notation, as simple as that. So I've taken the coefficients, written it like this in matrix A, then the unknown or the variables in matrix X, and on the right side I have the constant, which is the output over here. Whatever I have here, I put that. Same way I've written it here. And just as a recap, in one of the earlier videos where I was trying to teach the basics of matrix, you would have recalled that this matrix, which is on the left side, which kind of is the transformation matrix, is called as the coefficient matrix, because we are just stripping off the coefficients of the linear equation and putting it here. The xy will be called as the input matrix or a variable matrix, because the value of x and y kind of varies, and that's the input. Matrix A is going to transform the x kind of a thing, and B is the output constant matrix which we are getting. Same way over here, and in short form we can write it as A multiplied by x is equal to B, like this into this is equal to this. Okay, that's how we are writing it. Okay, so now what are we trying to say? I'm going to take this equation 7, which is highlighted in yellow, which is the value of x and the value of y. I'm going to copy it over here again. So you just focus on this part here. I'm drawing a line here. Okay, so this is the matrix that we have, the ABCD generalized form of matrix in the matrix notation, and then we have this value of x where the denominator is AD minus BC. So I'm going to just rewrite it differently. If you see here, I'm writing it dm minus bn and AD minus BC, and I know that AD minus BC is the determinant of this matrix from here, from this point. If you see here, this part. So I'm going to write, I can write either this, I can either write this way or I can write this way, right? In the matrix notation, simply ABCD. So that's how I'm going to write it here, over here. If you see the denominator, I've written in the simple determinant notation, right? ABCD, where we cross multiply this. So the interesting thing is, if I can switch back between this notation in the denominator, which is AD minus BC, and take it to a determinant notation like this, why can't I do the same on the numerator? Because numerator also has kind of the same pattern where two elements are being multiplied and then they're subtracted, right? So why can't I write about that? And if I try to attempt to write that in a determinant format, the numerator, if you see here, which I've attempted, so I've simply written m and n and b and d, and if you cross multiply on this diagonal first, it is md or dm, which I get it here, and then minus, I cross multiply or multiply the other two elements on the other diagonal, which is the forward slash bn ibn. So this is completely valid because that's what I'm pretty much doing in the denominator. So why can't I do it in the numerator, right? So if I do this way, now the new value for x, in a way, in a roundabout way, or in a different way, is nothing but a ratio of two determinants, right? One is at the bottom and one is at the top. The bottom one, I know it's a determinant of the given coefficient matrix. It's a determinant of this matrix, right? I know that. So that's pretty easy, and that we know. But how do I explain the numerator? What does it stand for? It also looks like a determinant, but it's a determinant of what? That's a big question. How do you think about it? So now just let's focus on only the numerator for the time being, okay? Not the whole equation, just to focus on the numerator. I'm rewriting it m and n and b and d. And if you recall here, the b and d is in this column and the m and n is here. And there is no a and c in this this mysterious numerator that we're talking about. So I've retained the second column, and the constant matrix, or the data elements in the constant matrix on the right hand side of the equation, I'm bringing it here within this, and I'm completely dropping a and c, which correspond to the x variable. For example, here, since I'm trying to find the value of x, I'm completely ignoring the coefficient of the x variables from both the equation and trying to replace it by m and n over here and keep this as is, right? That's what I'm trying to do here. So that's what this gives us. So in a way, if you want to understand what does this determinant represent, I can say that this determinant represents or it's kind of computed for finding the value of x. And for doing that, in a way, what I've done is I've removed the coefficients of x, which is a and c, and I've replaced by the data elements on the constant matrix, which is m and n, right? And this perfectly works fine, because that helps me compute the value of x. So what happens in that case is x becomes dx upon d, where d is the regular determinant of the coefficient matrix and dx is a determinant of a matrix or of a determinant where the elements representing the x variables are removed and replaced by the constant, and that's a determinant, which is what we are getting here. So basically determinant, the value of x in this case becomes a ratio of two determinants the way I've explained, and it's completely perfect, right? That's what we have done. There's nothing new, it's just borrowing from the same concepts and thinking it intuitively. In the past videos or when we are focusing so far on defining the determinant, we were completely focused and were laser focused on the denominator part. And now we are not only focusing on the denominator, but we are trying to also understand what it is doing to the numerator. And then we have realized that numerator also is a sort of determinant where we kind of bring in the constant matrix from the right hand side and replace it with the very value we are trying to find. Similarly, when we want to find the value of y, what we do is we'll keep the terms which are associated with the x variable, but we'll remove the y variable. In this case, the y variables are going to be b and d. If you see here, b and d, we're going to remove it, and we're going to replace this column by m and n again. So whatever values you're trying to find where the variable associated with x or y, you remove that and replace that with a constant matrix. And again, when you multiply it on the backslash first, followed by the front slash, which in this case will be an minus mc, which is what we have got from the previous side when we derived it, which is an here. The terms are on the other side, but it's the same thing, an minus mc or cm, right? That's what it is. Again, nothing new. We had these terms here, right? So we are just kind of unleashing a different way of looking at the numerator as well as a determinant, and that's what this brings us. So this piece which we are defining here, the x, value of x as a ratio of two determinants, dx and d, and also y, which is defined as a ratio of two determinants, dy and d, is nothing but Kramer's rule. Solving simultaneous equations, meaning finding the values of x and y in terms of ratio of two determinants, is nothing but Kramer's rule, and you can extend it to 3x3 matrix also. That's what pretty much it means, nothing more, nothing less. But this kind of gives an intuition why it is done in that way. Normally textbooks where they start is they come in the red portion, they say Kramer's rule is nothing but a ratio of determinants. But to give you an intuition where did this come from, this kind of session will help you of thinking of where this is coming from by solving the system of linear equations algebraically, and that's why kind of it's derived. On the left hand side, if you see, the answers will be the same. If you see over here, when we solve it in a traditional way, the x value is 2 and the y value is 3. And if you solve it in this way, it's going to be the same thing, because denominator we already know it's 7 because we already derived it here, right? It's going to be the same. The denominator of the coefficient matrix, it's going to be 7 in all the cases. And the numerator, if you see compute, where I substitute the constant values in terms of x and keep the other column same, and when I compute the determinant and divide it, it gives me the value of 2, which matches. Similarly for dy, it gives me a value of 3, which kind of matches. So this kind of a proof that the equation kind of works. All right, so what are we trying to sum up here as a closing comment, right? So what is Kramer's rule? For a 2x2 matrix, or even for a higher order matrix, 3x3 and so on and so forth, what we are kind of figuring out is the value of unknown variables. What we are trying to find, it's called as finding a solution to the problem, whether it's a value of x or y. It all means the same, whether you say solution to the problem, or if you want to invert this matrix. So basically what it means is the given equation is given in terms of y is equal to, if you see here, m is represented in terms of ax and by. But if you want to invert this, meaning like if you want x to be represented on the other terms, that's what is called as inversion. So finding inversion of a linear equation, or inverting a linear equation, or finding a solution to simultaneous equation, or solving Kramer's rule pretty much mean the same. So just wanted to tell you that part. So finding a solution to a system of linear equations using Kramer's rule pretty much means that you're going to take a ratio of two determinants, numerator and denominator. The determinant in the denominator is going to be the determinant of the coefficient matrix that we discussed, and importantly, this cannot be 0, otherwise solution will not be defined or it does not exist. The determinant in the numerator can be found by replacing the column which represents the unknown values. First you take x or first you take y, you represent that particular set of columns by the constant matrix, and then repeat the same thing for the other unknown variable. And as a quick check in the exam, when you solve the problems, you always get the final values of x and y that you get. For example, in this case, x is equal to 2 and y is equal to 3, and always put back those values in one of the equations, either equation 1 or 2. You can pick up any equation and try to see, if I put the value of x here and y here, does it add up to 1 on the right hand side? If that's the case, then your answer is verified and you're on the right track, else you can fix that. So always get in a habit of double checking when you get the value of x and y and putting it back in equation. So that kind of sums up the Kramer's rule. In the next set of videos, we'll talk about Kramer's rule for a 3x3 matrix, which is just a natural extension where you have, instead of x and y, you will also have z, and then you substitute z also. So z becomes dz by d. So nothing more fancy. And that kind of gives you a Kramer's rule, and we'll also solve some exam problems in the next video. Hopefully kind of you enjoyed the video. Stay tuned. I'll see you in the next video.